What? Darwinism, yes.
I introduced it, you can correct the slide.
Yeah, yeah.
But at least he's probably in the talk here. And moving forward,
Okay, hello. So as you can see me again. So I do have a brother whose name is Jonathan, but I'm not Jonathan. So this second talk, I'm going to show you something which is quite curious, and I'm going to do some mathematics and show you how we applied with one of my PhD students something which comes from biology. So this guy has actually done his master's in computational biology, and then he decided to do computer science, and he came up with all sorts of interesting ideas, and one of them was to apply a concept that he calls that is called the Mullerian mimicry to protect cryptographic implementations against secret leakage. So it's a bit curious, and let's see how it works. So let's first introduce this Mullerian mimicry. So what is Mullerian mimicry? Is when you have two poisonous species that have the same enemy, and what they do is that they evolve to look alike. So why do they evolve to look alike? Because let's say that one of my defenses is that when you eat me, I taste bad, okay? And his defense is that when you try to eat him, he bites. And if I look like him and he looks like me, whenever you attack one of us, we can capitalize on the bad publicity or the bad memories that we are creating in your head. Basically, when you killed one of my species and you try to eat him, you have bad taste in your mouth. So you say, okay, this one I wouldn't eat, and then he benefits of it. But when you try to eat him and he bites you back, then you get a bad memory, and then when you try to eat one of my species, you capitalize on that. So if we have a common predator, we have an interest to evolve to look alike, to capitalize on each other's defensive features. And I give you some very curious examples. So what you see here, you see a bee and a jacket. So the bee and the jacket, they look alike. And as a matter of fact, whenever you have a toad or a frog that would like to eat any of them, they could capitalize on each other's defenses. Okay, you have other, and they have nothing to do with each other. The bee, this one lives in a hive. This one lives alone. They don't belong to the same species, meaning you cannot cross them with each other. You cannot interbreed them. This one is even more striking. So you see here two ants, but actually, if you look at these ants, one looks very different from the other because it is a spider. This one has two antennae, and this one is using the two front legs to mimic antenna. So it really looks like an ant, but it's a spider. It doesn't belong to the same species, it doesn't have even the same number of legs. Okay? So why? Again, because this one has very powerful jaws, and this one stings. Okay, has a sting. So they capitalize on each other's defenses. And then you have also snakes, for instance. So snakes that look alike to some extent, and again with different species. And this one, which actually strangulates the victim, and this one that bites the victim. So if you are bitten or if you are strangulated, you keep it in memory. Another one is this butterfly. So here you have a butterfly which is called the monarch butterfly, and another one that really looks alike called the viceroy. And you can see that this Mullerian mimicry even misled human biologists. Why they call this viceroy? Because it looks like the monarch. Okay, so it means that they gave it a name which relates to the monarch, or it had nothing to do with each other. So you see, when you eat it, it has bad taste. So now let's go to physics. So in physics, what we're going to do is we're going to consider a very, very, very simple model of computation. We're not going to talk about block ciphers or string ciphers or public key encryption. We're just going to talk about the most basic information that you can do when you want to write information from one place to another. So here we have a microprocessor, and you have a piece of data D, and you write this data into a memory. And when you write this data into a memory, some information is being leaked out, and this information is some function of the data and of the time. Okay? So it can be, for instance, the power consumption which is being spent by your system. It can be the electromagnetic radiation that come out. But basically, in all cryptographic implementations, people care very much about this leakage of information. And we have this f of d of t, which is a function of your system and of the data that you are writing. So different d's will give you different... So basically, what is inside, if you want to look into what is in this leakage? So basically, you can see the system as taking some digital information as a function. This is this d. And it's giving you this f dt. And this f dt, if I look inside, this is what I measure. But inside what I measure, there are two components. There is one component which is the pure leakage. Okay, meaning that really what the system would leak. And then there is some noise. This noise is due to my measurement equipment, and it is used to the environment, not to my system. But what I measure globally is this. This is what my logical analyzer shows. But inside there is this pure signal of my system and some noise that comes from the instrument, that comes from the external world. And we would like to use this noise actually as a means to confuse the attacker and make him see different objects as if they look alike. So we'll see what happens. So basically, this is my system, this is my model. I have some additional information D, I get some measured leakage, and this is what's inside. We would say that we have here n bits, meaning that we just write n bits, microprocessor writes n bits into the memory, and then I can measure this leakage that comes out. And the idea that we had is the following. We're not going to modify the system in any hardware way. We're going to buy a memory that comes from Taiwan and a microprocessor that comes from Taiwan. And we want to secure this against leakage by doing the following way. In my memory here, in my memory on that side, I have n bits total. And I'm going to use my memory in a degraded mode. What do I mean in a degraded mode? I'm going to devote some bandwidth in my memory to store the actual values that I want to store in the memory. So I store the actual values here. These are the actual values. But I'm going to complete each of those values with some camouflage value v, which is chosen as a function of k, that has the property to make all leakage functions look alike. Okay? So for each value k, I have some magic camouflage value v. How do I find it? That's another problem, okay? But this is the basic idea, and this is what we go after now, okay? So as a defender, what I'm going to do, I'm going to sacrifice some bandwidth and memory storing capacity maybe to buy similarity between the leakage functions that we have here. Okay, so I'm going to sacrifice part of B. I'm going to cut the data into two pieces. One which is the real data, and the other one is just a redundancy, and the redundancy is going to be chosen to make all leakage functions look alike. Okay. So what is the analogy with what we have been talking about before? So here what I'm going to have is this K and V, which are going to be actually my D. D is now composed of K and V. Okay? And I'm going to have here the leakage function. And my defender goal is to select for each K a complementing value, V, okay, that will make the functions look alike. And I don't want to assume anything about my leakage function. So if you go to see someone doing electronics, you say, oh, look at the Hamming weight and equilibrate the Hamming weight, or maybe you can do some other models. I don't want to know. I have I'm like the attacker. I have an ability to acquire those functions. I have the ability to store them, to process them, and I want to know which to choose. Okay? So for K1, which is different than K2, I want those values to be such that this is as similar as possible as that. And this is basically the analogy that we have here, is that we want to make those two species really look alike, although they are different. So what do we have here? We have here a sort of genotype, which is the K1 and the K2. And then we have some genetic variability, which is the V of K2 and the V of K1. So I don't want to really fundamentally change the genotype of each of those species, but I want to modify this part to allow them to evolve so that they look alike. So how do I make it evolve? This is a good thing when you take a student, a PhD student coming from another field. So what we want to do is to be as discrete as possible and let the noise do the rest of the cover-up work. Basically, this ambient noise that I was talking to you about is just like if I want to walk and there's this grass in the savannah, and I want to just be so that the grass covers me. That's all I want to do. So I just want to be not to be too distinguishable. So basically, when those two snakes, they really look alike, if you look quickly and there is noise, you would confuse one for the other. You will not be able to distinguish them. So we decide not to attack. So here is the same thing. I have some ambient noise, and if they look alike, the ambient noise will not allow me to distinguish them. And if I'm unable to distinguish them, I'm unable to know what you wrote inside your memory. This is the basic idea. Okay? So to let the ambient noise do the work, I need them to be as close as possible. Okay. So let's consider a small example. So I have 4 bits, and I devote 2 bits to the payload data, and 2 other bits to the camouflage. Okay? So I have 4 bits on my bus, and I want to devote 2 bits to the data and 2 bits to the camouflage. I'm losing 2 bits actually, okay? So I'm going to call these bits colors. You will see why. So I have points of color 0, 1, 2, 3, and these ones are the genetic variety of the species. So here is basically what is going to happen. I'm going to have several populations. I'm going to have the population of the zeros, which is one species. I'm going to have the population of the ones, which is a second species, of the 10 and of the 11. These are 4 species that I have. And those 4 species, here you have, for some reason, this species got black, but it's blue. Okay, so you think that what you've seen here is blue, okay? This is blue. So you have this red species, this blue species, this yellow species, and this green species, and these are actually true species of butterflies that we found. And what I need to do is select one representative in each species. Now I let the species in nature, and they begin to evolve. They begin to look alike. So some of those will be eliminated by natural selection, some of those and some of those. And which are the ones that are going to be eliminated by natural selections? The ones that do not look like the others and hence cannot benefit from the millennial mimicry of the others. So what will survive in each group are, if you wish, the GCD of the populations with respect to the attacker, which should be some bird. Okay? So I'm doing mathematics here, we're doing I don't know what. So, okay, good. So which representative should I choose? Okay, so I can say, this one is really like this one. So I'm going to choose this one and this one because they really look alike. But if I do this, I pay a very high penalty here because those ones are very different from those that I have here. So I can choose 2 very similar butterflies here, but they're actually, so here the gain is going to be high in terms of similarity, but here the penalty is going to be high. So how do I choose them? So for instance, you can see this choice, where you can see that you have some yellow here, some yellowness, and here you have some yellowness, and here you have some yellowness. So you say, I'm going to take this one, this one, this one, and this one. So the magic V values are going to be 11 for 0, 0, 11 for 0, 1. It's going to be 0, 0 for 1, 0, and 0, 0 for 1, 1. And this is how I'm going to transmit my information on the bus. When I need to transmit 0, 0, I will complete it was 1, 0, 1 was 1, 1, 0, 0, 0, 0. And then what you will see those butterflies flying up. You see, I don't know if it is this species, this, I don't know what he's doing. Okay? And the criterion is that I want them all to look alike, and here the notation that I used is very bad. Because in the notation that I used, I'm not going to, I said that this should be similar to this, similar to this, similar to this. It's actually all of them should be similar, because if this is similar only to this, it can be quite remote for this one. But I needed to place them in a line. So basically, this abuse of notation means that they all look alike, okay? But this one should look alike this one as well. And this is the analogy that I gave. The least significant bits are mutations, and the MSB is the basic genotype, and this is why I call it the color, okay? It's the main feature of them. And the other side is the mutations. Okay, good. So far, so good. So how to find the good one? So first of all, to simulate the mutations is easy. You just list the numbers, and you measure what is the F functions. Okay, so you need an oscilloscope, and you generate data and you measure. So this is easy. Okay, but measuring similarity is not that easy. So assume first of all that you have a blue jay, the bird. That has only one criterion. It can only see the intensity of yellowness in the butterfly. So it can only measure the degree of yellowness. So here you can see what I added is how much yellow there is. So you see that the one here that doesn't have yellow at all, it has a yellowness 0. If you have a little bit of yellowness, you have 1. And then you increase, and you have those who have a lot of yellowness or very yellow, there are 9. Okay. So the blue jay, the bird, it looks at the butterfly and sees how yellow it is. That's the only criterion that it has. So if this is the only criterion that the blue jay can exert, here is the algorithm how you choose your candidates. So first of all, I sort all the butterflies in my collection, all species confused, on the scale of yellowness. So all those who have no yellow at all, I put them here, a little bit of yellowness there, very yellow here. So I put all of them there. And you can see that I mix species actually. The red species is here, the blue one here, the green one here, that's all spread. And now what you do is you need to find, on this scale, the shortest possible segments that contains all the colors. Okay? Basically, I'm trying to pack all my colors into the shortest possible segment. So let's see how we do it. So I can say, I keep an optimum. So first of all, do I have all the colors in the segment 0? No. Okay, I don't have the yellow, I don't have the green. So I extend it. Do I have all of them? No, I don't have the yellow, I don't have the green. Do I have? No, the yellow is missing. Okay, here, yes. So the current optimum is this. Then I try to see if by restricting it on the other side, I keep my optimum. Yes, I keep all of them, so I found a better optimum. And now, if I shorten it further, I see that I lost my optimum because I don't have it. So I keep the last optimum, and then I increase it again. Okay, and then I find other optima. Okay, again, and I didn't find. So then, what do? I said, okay, this is my segment, the smallest possible segment that contains all the colors. And I said, this is where I'm going to play. So I'm going to take a representative now in this segment, a yellow representative, a green representative, a red representative, and a blue representative. And these are going to be the data that I'm using. So this means that my attacker, he can only see one point. Let's say he can see the global energy spent during the data transfer. That's all he can see. Okay? He cannot measure the energy spent at 2 different moments. He can only at one. Okay, this is the degree of yellowness. Okay, so this is easy. Now, what if you have a blue jay who is more perceptive? Let's say one that has like laser eye, a bionic one. So it can see the size and the yellowness level. So this one, he can see size and yellowness level, meaning that he will not confuse a big butterfly with a small butterfly, although they are as yellow as each other, okay? So the first question, that how many units of yellow worth 1 unit of size? First question that you need to settle, which is not evident. And the other question, which is non-evident at all, even if you assume that 1 unit of yellowness, no matter how you measure yellowness, is equivalent to 1 unit of size, you have still the problem of independence, meaning that the criteria that you're measuring can depend on each other or can even be negatively correlated. Let me give you a simple example. If I'm measuring size and height, okay, how high you are and how heavy you are, well, you can see that people who are high are usually heavy. Okay, so there is a correlation. So if the blue jay actually measures height and weight, okay, so a butterfly comes and you say, okay, now weight butterfly, how high you are, I want you to go on this weight, how many grams you weigh, so, and then I decide if I eat you or not. So if the blue jay does this, you can see that actually the blue jay is measuring twice the same root cause. It is going to measure two quantities that are correlated to each other. Okay, so how do I take this correlation into account? And it might be that the correlation might also be negative. Okay, so sizes are hard to distinguish when yellows are not, and conversely. Okay, I don't know what is my population and how my memory that I bought in Taiwan behaves. So what we will do is that I'll show you how to deal with it, but for the time being, just for us to fix ideas, let's assume that we have independence and we have equal weights. Okay, so yellowness and size, we know how to deal with it, and they are independent. Okay, so now this is our problem. So what happens now? Each point, okay, is a side channel curve with 2 samples. So I write some value k and v of k, and I get this curve. This is a curve that gives me the power as a function of time. I was writing 17, and I got this funny image here. It's the trace of 17. But I'm measuring it at 2 different points in time. I'm measuring the power at this point in time, and I'm measuring the power at that point in time. So I have actually 2 measurements, okay, like yellowness here and size here. Although both of them are expressed in terms of power, for me there are 2 points, okay, there are 2 points of the same physical phenomenon. There are 2 features of the same physical phenomenon. Now I'm going to look at this point, at this curve, differently. I'm going to look at it on a power scale. What does it mean? It means that I'm going to give to this curve the first coordinate here and the second coordinate there. So I'm going to take those two values, and I'm going to project them here and there, meaning that this point here is going to represent this big curve here. Because the blue jay is acquiring 2 samples, not 1 as before, but 2 samples, this one and this one, so I'm going to represent the curve as a point, as this point, this gray point. And basically, when I do this for all my points, I'm going to have different curves. So you can see that the curves are quite different because I'm acquiring different data. And for each of these data, I have sample 1 equals that, sample 2 equals that. Sample 1 equals this, sample 2 equals that. Sample 1 equals this, sample 2 equals that. Each curve is represented here. And now, what is my problem? I put the colors, as I showed before, on the family of the red, the blue, the yellow, and so on, and I need to find the smallest circles that contains all the colors. So that's the generalization of the problem that I've shown you before. So I give you a constellation of points of different colors, and I tell you, now find the circle of the smallest possible radius that contains all the colors. So this is the problem that I want to solve, okay? And here, this is the level of yellow, and this is the size. The level of yellow is, let's say, 1 power measurement, and this is a 2nd power measurement in time. First, second. So if you generalize it to several measurements, let's say you have 3 measurements, and then you need to find the smallest sphere that contains all colors, okay? I asked Mathematica to draw to me a constellation to show you what happens in 3 or more dimensions. So my problem is this one. How do I find actually this solution? the smallest circle containing all colors. So I show you how this can be done using various algorithms. Some algorithms that they do not guarantee to you a result, but they work quite well when you have a quantity of information coming from physical measurements. So how to do this and at what cost? So let me show you the basic algorithm that we applied, or that we applied with success. So first of all, it is a sort of a divide and conquer. So how do you solve this by divide and conquer? So the first thing I do is that I find any solution. So I just take one point and I begin to go away from this point. I take a random point. I take this yellow point here, and I begin to advance until I find some other colors, and I find red. Okay, and then I continue to extend it and the radius. Now I found this, I found that, and that's fine. I got a solution. Okay, so this solution is not the best solution, but it's a solution. Like I do this. Okay, so now what I'm going to do is that I'm going to use this solution as a basis for my divide and conquer. So it's very interesting to see, for those of you who are into number theory and so on, don't doing that much divide and conquer, how those things are applied. So we call R the radius of this big sphere, this circle, and I'm going to use R as a parameter in my algorithm. So first of all, I'm going to define the plane, which is the smallest enclosing box that encloses all my points. So I basically take this point, and I put everything in a big rectangle. And now I'm going to halve this rectangle. Halve it into two. Halve it. Cut it into two. Sorry. Cut it into two. And I'm not going to divide it like this and solve my instance here and solve my instance there, because I have here a problem in this middle area here where I can have half a solution. And as a matter of fact, what I showed you, a solution is somewhere here. It is somewhere here. So if I just cut it, it wouldn't work. So what do I do? I just add r plus 1 over 2 units here and r plus 1 over 2 units there, r being the solution that I have already. And I'm going to halve it, but with some overlap. Basically, I'm going to have a first instance which is here, and a second instance which is there. And I'm going to solve separately each of those instances. So what is the idea? The idea is that I could indeed have a solution that hides somewhere in the middle. If the solution didn't hide in the middle, it was not in the intersection area, if it was somewhere here, I don't care. Okay, I preserved it. If it was here, I don't care, I preserved it. Okay? But if it was somewhere in the intersection area, okay, it means that I could have lost it. But because I take r plus 1 over 2, I know that whatever I would lose can only be worse than what I know already. Meaning that because I'm looking for the smallest possible circle, okay, what I could possibly lose is not anything that would be of interest to me. Okay? So I'm separating this into two instances like this. I find optimum in the right, I find optimum in the left, and then I repeat the process. Okay, so I have two sub-problems, okay, to solve, and as you can see, those two sub-problems have some intersection. This constellation here, you can see you can find it here. Okay, so this green, this red, okay, and then you begin again and again. Now note that you could also do this on several dimensions. You could not only cut here, you could also cut here, along this, and reduce again and again and again. Okay, so the interesting property is that the minimum solution to a problem is the minimum of the minima, okay? And you iterate the process, cutting along two dimensions, if you wish, until you reach a fixed point, meaning that by adding r plus 1 over 2 compensates halving, and then you solve each sub-problem by any algorithm that you wish, and compute the minimum over all your solutions. So in higher dimensions, you can find readily available tools that can do that. There is some German guy who wrote a software called Miniball that can allow you to solve this using different heuristics. And we actually applied it, and and this is the output of our program. So you give it a constellation and it finds this quite efficiently. Of course, you can generate pathological instances where you group all points here and all points there, and you force the program to find a huge circle, but for more or less randomly scattered data, and you can measure the scattering using measures like the discrepancy, for instance, and so on. And of course, we're familiar with the discrepancy. Measures actually the rate of dispersion. You can show that on the average, these algorithms are efficient. So what happens if you have an infinite dimension? The problem can be modeled in terms of distances between functions. We'll not get into it, and we are now ready to settle the question of dimension units, take correlations into account, and justify the Euclidean distance. Because I told you that the points that I'm using need to be close. But why am I using Euclidean? Why not a Minkowski of whatever degree 7 or Manhattan distance? Why Euclidean? Where it comes from? Just because we are living on an Euclidean world, we need to be Euclidean. So okay, so let's start to see how we evaluate the distance. So y is the yellowness level and s is the size, okay? So what I'm doing is that I'm evaluating actually yi minus yj and si minus sj, okay? Which is basically the distance between 2 points. So if the distance between the sizes is small and the difference between the yellowness is small, then I say the two butterflies are close. There is no brainer. And it's also here there is no brainer. But the question is what happens in those cases and how I deal with them. So basically, how many yellow saturation units worth one millimeter of size? So basically, it's like comparing apples here, and tomatoes there. So the solution, as you could have guessed, is to compute just a normalized distance dij, a square distance dij, which is basically the difference of yellowness divided by the square of the sigma of the yellowness, and this same thing for the size, and then to compare by increasing order of those dijs. And as a sanity check, you can see actually what happens. If you have only one dimension, meaning that you are not dealing with this anymore, this is being a constant, and here you have a square. So basically what you have is simply the absolute value of yi minus yj, which is exactly the distance that we had on our graph. Now, where this comes from? Okay, this you have seen this in the past in the exponents of exponentials, and this comes actually, you can have a look at the paper from the statistical analysis that we are doing. So you see why the Euclidean distance actually relates to the noise model that the natural noise model that we are using. Okay, so now what happens if the yellowness and the size are not independent? Well, basically you correct it. That's classical. So what I'm doing is that I say, okay, if now I have three things. I have size, weight, and yellowness. You can see that there is no correlation between yellowness and size or yellowness and weight. There is no reason why. But size and weight, as I told you, are correlated, okay? So then you know how to take this into account by using this rho, which is non-zero, to correct actually your score. And as you can see, you can subtract here the correction factor that allows you to not count twice the contribution of weight and size. Okay, and you can see that this factor that you are subtracting is actually taking into account weight and size only. Okay, it doesn't take into account the yellowness directly. Okay, so it is easy to generalize this with more correlation. So you can see this in the full paper I can give you. And the Euclidean distance actually stems from the assumed multidimensional Gaussian distributions, and you have 2 pages in the paper that show how. Okay, what is more interesting is a real-life experiment. So What we did is that we took here a memory, a RAM, and here a bank of registers. And what we do is here, using this, we are actually putting a value here, and we're triggering here the writing on the bank of registers. We're measuring the power consumption, and try to find what is going to be the best encoding that we can use here. So these are the results of our measurements. So here what you can see, we took 3 samples. So sample 1, sample 2, sample 3. So this is all power. So it's power, power, power. And when you write different values, you see that the green values were scattered like this, and the red values like that, and the blue and whatever. Okay, so they're all here. And when you took all these 3 and you collapse them into a 3D, is this. And when you run the algorithm, this is what it gives you. So basically the binary value of k, so you have here the values that are here. Okay, here. These are the v values. These are the v values. The v values are the ones that are not underlined, and the k values are ones that are underlined here. Okay. So you can see that we pack them into a sphere which is centered around this point, a specific point in space, has this radius, and these are the distances of the different characteristic points to the center of the sphere, and it is much easier to see here. So the 4 points that we chose that are packed into the smallest possible sphere are these points that you can see here, and that are here on the cloud that I showed you before. So basically all those other here were sacrificed for the sake of keeping those points here and using them to encode information. Now you would say, David, why do you impose on yourself to use only part of the encoding here, meaning that you could say, I don't care to have 0001 or 1011. Just take the 4, use actually the 8-bit bus, and take the 4 points that look alike, the most look alike, and to one arbitrary assign the value 0, to the second assign the value 1, to the third assign the value 3, and 4. Well, if you do that, it would work from a theoretical standpoint, but in practice you would need a decoder, meaning that you would need some hardware device that will interpret that. And this hardware device, when you try to build it, leaks information. Okay? Because you need to pass it through a table to know what is the result, and this table should give you some result. So you could as an option said, okay, I'm going to find 4 points here, some 4 points in the middle here. I would look for them here. And I really want to find four that are very, very close. The first is going to be arbitrarily assigned to the pattern 00, the other 01, the other 02, the other 03. You might not have 01, 02, 03 readable on those numbers. But then it's the receiver's work to decode them. The problem is that once you do that, you don't have your information. And to interpret this information, you have to pass through a hardware device that leaks information. And then you run after this hardware device again to see how you can find a decoder that decodes in a way that doesn't leak. Okay? So here we stopped actually this at 1 iteration. So basically, if you're interested, this we have several signal processing, statistical, combinatorial algorithms that arise from those kind of simple problems, and there's still plenty of cooperation possibilities on that, and you can go to conferences such as CECC and so on where people deal with those things. So I hope you like this second talk. It was not really crypto, but in the periphery of crypto, but it's nonetheless a bit interesting. Thank you. So my third talk is going to, sorry.
So this is like designing something for analysis, okay? But I think you make some of the wrong assumptions. The problem, and you can also problem is the okay? So I think And there is a better variant, not really have to talk about the prefer, but you make a population of different programs, with different verbs, and you make them evolve, and you kill some of the
Yes. Yes, what you say is very interesting because, as a matter of fact, there is this company that does the licenses these countermeasures against these power attacks called Cryptography Research. And I visited them a while ago, and they showed me something very interesting that they have really in the sense of what you say. They have a design, they have a simulator of power attacks, so it simulates the DPA. So you give them an AES design, and the AES design is run, and they simulate the power consumption, and it gives you power consumption curves, and they run an attack automatically, and they distinguish, and so on. But then they have in their design a number of parameters that are not fixed, meaning that they can say we use this number of bus. They have several parameters in the design. And what they do is that they have this parameter, they fix this parameter. They don't know how these parameters, when you fix them, they're going to affect the power consumption. You can do it by simulation, but you cannot predict in a formula. And then once you got this effect on the power consumption, you don't know how it's going to affect the DPA. So what they do is that they set a value to those parameters. They run the simulate. They generate the instance, the hardware instance, because they fix these parameters, hardwire them. When you say I want a bigger bus, it's not that you fix some parameters. It's really that you cut wires and you. So they do this. They run the simulation, they run the attack, they see the result of the attack, and then automatically they feed it back into the design, and they say, okay, in this branch we were going into some sort of backtracking, so it is very unlikely that it will improve again because we are just going on the wrong gradient, and then they launch it again. And like this, they end up with designs that are automatically optimized to resist DPA. It's exactly what you say. I don't know exactly how they just saw me a demo. But I do know a guy, his name is Rodrigo Portela, who works there, who is in charge of this project. And it might be good that you talk to him because... No. No, cryptography research, okay, so this is a question which is go even beyond that. Actually, what happens is that these people said that they invented the power attacks, and then they came to license to people, and people just wanted to avoid the lawsuits and ended up by the way in which they sold their licenses is quite astute. Is that instead of you're manufacturing cards, so instead of coming to you and telling to you, please buy the license from me, I'm going to see your chip supplier. So you are manufacturing cards, but he's an XP, and I'm not going to bother you. So I'm going to come and tell you, listen, you are going to tell to your supplier that he needs a license, because if not, I'm not going to buy from him. And if I give him a license for free, then you can use him to scare him to take a license from me. So this was basically the game. So the first company was Renesas. Renesas got a free license. And then the card manufacturers were told, okay, tell our suppliers to go and see Renesas and tell them that you're going to buy only from Renesas. So the others, ST and XP, say, oh, why are you going to buy from Renesas? We also want it, but you don't have the license. Go to CECC Cryptography Research. So this is basically how it... Yeah. Because as I said that basically it turns to the question of Nicolas. Basically, I know what the attacker. I want to protect myself against an attacker that does two power measurements. Okay, so let's see where it is here. So I can have here 2 points. I can have 2 points, and these 2 points might be correlated. You might have a correlation between the two. You see that if my points are, let's say, very close, there might be it might be the same information that actually affects the two points. So I really need to know how much the value at this point is correlated to the value of that point, so that I don't measure twice, so that I don't take into account twice. If I want to, let's say, if I want to know if you and him are similar, okay, I can use different features. So I take the height, I take the color of skin, but if I measure you, if I go and measure you on features that are correlated, it is as if I'm giving you similarity points on the same criterion several times. You see, this is something which is used in many cases in industrial control, for instance. If you look in the space shuttle, when they send the space shuttle has a lot of sensors inside, notably temperature sensors. Now, the problem with temperature sensors is that if I put a temperature sensor here and put a temperature sensor here, you see that if this one tells me there is an alert, it's too hot, the probability that this one tells me that there is an alert and it's too hot here is also very high, because they're just nearby. So basically you're measuring nearly the same information twice. So once you measure all that, what do they have on their control screens in NASA? They don't have all the sensors to know what is going wrong, because then they will have an overload of information. They have 1,000 sensors that tell them that there is a problem. So what they do is that they take the sensors, they remove the correlation, and they distillate it into independent phenomena, meaning that whenever there is a correlation between the measurements of two sensors, when they do their experiments on the shuttle, they correct it using that way, so that if you have a fire at a given place, you will not have just 1,000 indications, but one indication which will be representative of what happens there. And here it's exactly the same thing. I assume that I know how the attacker is going, what is the resolution of my attacker, how much the attacker is going to, and I really need to know, based on this resolution, what would be the visible correlation that will disturb him using the curve that he's reading. Yeah, but it is, I search the space anyway, but the power scale here is scaled as a function of the correlation. You see, you brute force the space anyway, but this is power times a given coefficient. This is power times a given coefficient, and the others, I don't know where is the other one. This one, power times is a given coefficient. Okay, you have to count for the variability that this sample depends on that sample. You see, because if not, what I would do is that I would count again and again and again the same information. Basically, if those two samples were very close and the third sample was very far, you see, I wouldn't want to say that two things are very close just because they appear in two samples that are a few nanoseconds one after the other. It means that I would be counting closeness points for things that are not close just because you do measurement, and then measurement. So if you do measurement, and then a third measurement here, I wouldn't want the distance between those two to count as much as the distance between those two. You see what I mean? Well, we can talk about it if you wish.
Thank you very much again.
I can do a short talk in 7 minutes.
Pronounce your name.
Naccache. You are from?
Hungary.
Hungary.
You married from French?
No. My family is actually